Have you ever wondered, how can I make the most money from exploration in Elite Dangerous without having to go to stellar graveyards and farming neutron stars? Are you maybe a fleet carrier owner in the middle of nowhere and thinking, where can I find tritium? Well, in this video, I'm going to tell you all those things and give you a little bit of an insight into the Elite Dangerous galaxy. Firstly, I should introduce myself. I'm nobody really special in the community, but I am a particle physicist by profession. I went to university largely because of Elite 2 inspiring an astronomy spark in me as a young boy. The stars fascinated me, and in the end, I did something different other than astronomy, and I am Eros Madeline. Now, this sounds like I'm going to make some statements and lean on the appealing to authority fallacy, in which I tell you something and I want you to believe me because I have a PhD. But that's not really what's going to go on. I'm going to show you plots and I'm going to back everything up with a little bit of data analysis. So, with that said, let's get stuck in. So what I've done is I took 4 weeks of EDSM data dumps. Roughly that equates to around 2 gigabytes each. And I wrote a statistical analysis and parsed a lot of data, obviously, in the process. It equates to roughly 1.1 million stars in total, so pretty decent statistics. And I wanted to figure out a few things. Initially, I did this not knowing that it'd already been really taken care of over at EDAstro by Cmdr Orvidius. Hopefully I got the pronunciation correct. I did this largely because I'm taking out a fleet carrier exploring, and the first thing I wanted to do was make sure I could find icy rings. Obviously I can stumble across icy rings, but I wanted to really know where is the best places to look. Not only that, but if I'm also to do my upkeep of the carrier on the basis of exploration, how can I get the fastest return for my time? So, in a way, I redid all of the work which Cmdr Orvidius did, but I still want to pull it all together and point out a few things in an exploration guide of sorts. I'd actually gotten through most of my analysis before I was pointed at EDAstro by a fellow commander, but the good part is that Cmdr Orvidius and I came out with roughly the same global conclusions. I checked a few things on his forum thread, so I feel okay about presenting this and not feeling like I stole anybody's work, since I did do the data analysis myself. So, the data itself are bodies weekly dumps from EDSM. This is in JSON format, and so the first thing I did was to sweep through and grab all of the system IDs for all the main stars in the batch, along with the stellar class. Then I would run over the whole set for each body and match its system ID to a star and thus the stellar type, and add it to a histogram. I did some other things as well, such as trying to figure out which stars don't have any other bodies connected to them. And so when I normalize things, and I'll talk about what I mean by that, when I normalize things, it gives you a representative picture of, if you find a star with planets, how many planets can you expect? It's not a, if you go and see a M-class star, on average, this is how many planets there will be there, because there are, of course, lots of M-class stars with no planets at all. So with this said, let's go and take a look at a couple of plots to prime the rest of them. So we'll start off with our stars. This is a distribution of stars in the sample. And I've got the main sequence stars separated, the O, B, A, F, G, K, and M stars. And I have brown dwarfs all bunched into one, T Tauri all bunched into one, the same thing for white dwarfs, neutron stars, and black holes. Now, there are obviously other stellar classes, and I ignored those. So these are your carbon stars and things like this, because they're rare and they're typically interesting places to look anyway. So on this plot, the light pink is the total number of stars in each stellar class, and the darker red is the stars with planets. And so what I mean by normalize, what I'm typically getting at is you divide the number of objects by the number of stars to give you the number of objects per star. Now, what I can tell you from this distribution is that brown dwarfs are undersampled. This is perhaps natural because there is a natural bias against brown dwarfs, mostly because for any commander out there who's done any exploration, brown dwarf class stars systems are pretty boring. So not many people scan them. The other star systems have lower statistics simply because of the rarity of the stars. There is, in fact, a real dip in G class. I'm not totally sure where it comes from. That was one of the things I checked with Orvidius. So this sample is also, because it's the last 4 weeks, I'm pretty confident this represents a general general trend throughout the galaxy in Elite. And the reason why this is good is because the player bubble, or the populated bubble, has a lot of hand-placed stars, and it's got a very different distribution compared to deep space. And so that's why I took this approach. The first piece of analysis is to simply divide the stars with planets by the total number of stars in each class. And this is what you get. And so I've highlighted the main sequence here, and I can roughly say with fair confidence that the distribution is very nearly flat at 45 to 55%. The underrepresentation of planets in O class, I feel, is natural. It's quite disappointing when you find an O class and jump into it and it doesn't have anything around it. But I feel that's kind of common. So it's not necessarily sampling bias. And so, yeah, this basically tells you that roughly 50% of the stars in the galaxy have planets of some form. And if we look at it on a stellar evolution standpoint, it makes sense as well that brown dwarfs and T-Tauri stars have fewer planets, mostly because T-Tauri are protostars. They're very young, and so that makes sense that not many planets would form around them at that point in time. And same thing for brown dwarfs. Perhaps we expect large amounts of stellar debris and ice around brown dwarfs, but not large bodies. And this seems to make sense. Okay, so with that said, let's dive straight in and go through each planet type. So this is icy planets versus stellar class. And as you can see, this is already normalized. It's the total number of planets per star. And this is where I give a little bit of a rant about people shouting RNG, because what I see here is strikes me as a physicist as a probability distribution function for icy planets. Now, what this shows you is that the distribution of planets is not random, it's deterministic. And the devs have already stated previously in the past that the stellar systems are generated based on a planetary simulation, in which you start with a mass distribution and angular momentum distribution. And then you can do your dice rolls, and depending on a few parameters for the type of system that you're in, and things like the amount of heat, total energy, you then can place your planets and make sure that the orbits are stable. However, the reason why I'm mentioning probability distribution functions is that you could take these plots that I'm going to show you and write some kind of system, maybe like a Poisson probability, where you can place planets in terms of numbers of planets per star and pull out exactly this plot and create a fake galaxy which looks very similar to that in Elite Dangerous. Although if you did that, you wouldn't know anything about the orbits. Anyway, let's carry on with the actual discussion. Here we have proof that the hotter the host star, the less icy bodies are in a system on average. This makes sense from a physics standpoint. You'd not expect a super hot B-class star to have lots of icy worlds. And in those hotter systems, you would actually expect your ice line to be further out into the far reaches of the system. In the far reaches of the system, the stellar disk, which the protoplanetary disk, which forms the planets, naturally takes longer to accrete material. And so your planets, which are icy, probably haven't formed yet or won't form. Okay, so moving on, we have rocky ice worlds. This is a hybrid class between rocky and icy, obviously, hence the name. And what we find is a probability very similar to that of icy with a bit of a shoulder. And we're still peaked, however, in the M class. These planets are really awesome. I always like going to see them because they always have interesting geology. And from time to time, I've also found that they've got extreme features as well. Moving on to rocky worlds. Once again, we have proof of non-randomness. And we have a distribution which is almost flipped in comparison, or almost exactly flipped in comparison to that of icy worlds. And again, on RNG, a small note on Engineering 1.0, if you've ever heard me rant about it. The average distribution between B and M class is actually very similar to the average 1.0 style engineering probability function. So let's say you rolled your engineering upgrade and you got the equivalent of a K class roll here. There'd actually be little to no point in trying to roll again because the probability of you getting a roll to land in the M class here is actually quite small. And I feel that it's a little bit of a shame that the community didn't understand this, that they continuously said it's totally random, when it really isn't. I think the problem mainly is that the user interface was not designed to really tell you this. If it had done, perhaps the community would have really understood what was happening, rather than just simply shouting RNG, RNG, because a few salt farmers like to do that. Anyway, sorry, I'm supposed to be talking about exploration, not ranting about engineering. So what we see here is that the most heavily populated systems with rocky bodies is B through F class. And that makes sense. You'd expect less icy worlds, more rocky worlds. Now we go on to the more juicy things, such as high metal content worlds. Very similar to rocky, only that they are more populous in general across the hotter classes. And again, we have a weighted distribution somewhere toward B through F. There's a peak in neutron stars. I'm not totally sure why that is. It's possible that the model which generates stellar remnants has something about stripped gas giants. So maybe they're modeling the cores of gas giants which have had their gas essentially stripped away during a supernova forms high metal contact worlds. I don't know. Next is metal rich. Once again, you can see how weighted in general the distribution is here. Very heavy bias towards hotter stars. And here you have O class stars as being the most populous. Based on experience, these are also grouped around nebula, which is probably responsible for the sort of shelf-like shoulder going from A through K class. Now, the other thing I did is I got lazy with gas giant worlds, since I don't really see them as being particularly interesting in terms of the different classes of gas giants. This is all gas giants in one sum, and what you can see here is that the distribution is flat. The distribution is basically 1 per system for most classes, with a bump in B, where you go up to about 2. Then a very high population density in protoplanets and non-sequence stars. All right, so now for the exciting ones. These are water worlds to start, and maybe this is what you would expect. We have a bias which follows high metal content worlds, but there's a cutoff for the 2 hottest stellar classes. Again, you want to be able to form a rocky planet of some form which has materials on it, but also it being a location in which you can have liquid water. So here we're looking at A and F classes as being the best possible places to look for water worlds. Notice the odd distribution in non-sequence classes again. Strange. Next up is ammonia worlds. Very similar distribution compared to water worlds, with higher contributions in G and K, so you have more of a shelf rather than a high drop-off. I think you'll probably guess that we should see very similar behavior for Earth-like worlds that we do for water worlds. So, without further delay, this is water worlds. And so what we do see is that the distribution is almost, but not quite, identical to that of water worlds. So what the real difference between water, Earth-like, and ammonia worlds is more to do with the chemical abundance in the system than it is anything else. And that makes sense. On the non-sequence classes, such as neutron stars, I'm not totally sure why we should expect a good distribution of Earth-likes in neutron star systems. Maybe this is selection bias. To me, the physics doesn't really make sense. The environment around a neutron star is going to be very harsh. You'll have very powerful radio waves and microwaves. Not only that, but anything which is accreting material, which would be quite common for a neutron star or even a black hole, you'd actually get a lot of X-rays produced as well. And I don't think that makes for a very happy Earth-like world. But anyway, this is what we have. It also surprises me that we have Earth-like worlds in black hole systems. However, my analysis doesn't really care whether the Earth-like is orbiting the black hole or orbiting a binary star. So it's possible that this is actually binary stars. Next is our terraformables. So terraformables I took as all types of terraformables. So whether this is high metal content, rocky, icy, or water world or anything, I just took them all and counted them. And so here we see almost identical distributions to water worlds. And again, I don't think this is unexpected. I think for a planet to be terraformable, you want the conditions to be almost identical to that of a water or Earth-like world, although maybe the chemical composition isn't quite right. So, if I was to summarize things into a Eros Madelung's exploration guide, I would basically tell you that if you want to make the most money and you're in the middle of deep space, so that is not in a neutron field, you should be looking for terraformables and scanning those, water worlds, Earthlikes, and Ammonia worlds. And here, basically, you're looking at the highest probability as being A and F class stars. Maybe G if you're feeling lucky. Now, at this point, I'd also like to post a caveat that please don't only scan A and F stars. I think explorers should really try and map locations and try and get a good sample of all stellar types. So, yeah. I say go out and scan A and F systems, but please scan all systems. Now, what else can we pull from the data? Now, I mentioned if you are an explorer with a carrier and you want to find a tritium, where can you find the tritium out in the galaxy? Well, the obvious answer to this is in the icy rings. So this is icy rings of all types. Again, I did not differentiate whether these rings are around gas giants or around other planets, but I just counted them all. So here we see weighted distribution in our very similar to our icy worlds, where you would again expect colder systems to have more ice. So K and M are your best bet. If you're near a stellar graveyard, then white dwarfs for some reason, that's fine as well. And not to leave anybody else out, for your metallic ring seekers, I've only shown the metallic ring. However, the distributions for rocky and metal rich are basically identical to this. And again, we have a bias towards hotter stars. We do have a weird non-existence of rings around O-class stars. I'm not totally sure why this is, because I could have swore I have seen rings in O-class systems, but anyway, apparently my data analysis did not find any. But in general, the trend you're looking for is the hotter the system, the more metallic rings you tend to have. So for all your painite miners out there, you're looking at B and A classes to find those metallic rings. So in a few final words, thanks a lot to EDSM for those batch JSON files. I'm grateful that you host them, and I'm grateful that you update them. Thanks again to Cmdr Orvidius of EDAstro. Sorry if I might have seemed like an overzealous high school teacher checking your work, though that was never my intention. And in final words, if you're exploring purely for money, A and F classes are your best bet outside of stellar graveyards. The probability of hitting a high value planet or group of planets is significantly higher in those systems in general. As an anecdote, I hit an F-class star system last week, and it had 2 water worlds, an Earth-like, and a few terraformables, and in total its value was around 9.5 million. Now, given my upkeep of my carrier in general is around 15 million, you can see that I was quite a happy camper with just that one system. This plot backs up also what I'm saying. This is the mean non-first discovery scan everything credit yield per stellar type. Now that's a very long-winded sentence, but what it means is if you add the value of every object in a system and you weight that with the credit balance you should get from scanning the average one of those objects, this is how much you can expect to get paid per system. And as you can see, you're looking at the bias towards A and F classes. Not only that, but for all you stranded carriers out there, If you want to hit up the K-class star systems, you'll get your best chance of icy rings and tritium. For the heavy metal miners, your B and A classes will do. Thanks for watching, and if I've missed anything or you have any juicy information which I might have missed, please let me know in the comments.